So in the previous lecture, we have just started the concept of solution. We did some basic definition concepts of various kind of strength of solutions. So basically we defined concentration terms. If you have not gone through that lecture, please go through that lecture because the upcoming chapter will have a lot of application on those concepts. Okay, so till now we have covered the complete chapter of chemical kinetics. I hope you have solved the entire daily practice problem sheet and we have started with the next chapter, that is solution. Okay, so before going into the solution, the main concept which we wanted to talk about today is the concept of vapor pressure. Okay, now what do we mean by vapor pressure? Because in most of the 11th class we have encountered this term known as vapor pressure. Okay, mostly when we were dealing in the gaseous state chapter. So vapor pressure simply sounds that it is the pressure exerted by the vapor. Partially it is correct, partially it is incorrect as well. So let us enter into the concept of vapor pressure. Okay, so let me just start with the basic idea of what exactly is a vapor pressure and how vapor pressure is determined experimentally. Okay, so let us look at this beaker. We know that this contains a liquid. Okay, right, you can see this, that is in the gray color. So basically it is containing a liquid. Now we know that whenever we will leave a container of water, open container of water in air, the water will get evaporated and slowly all the water molecule from the surface will keep on rising and eventually they will escape into the atmosphere and ultimately the amount of the water in that container would decrease. Okay, so evaporation is a spontaneous process that happens by its own. Now the next question that should strike in the mind is why does evaporation happens? Now if you look at the liquid surface, okay, there would be molecule at the surface of the liquid and there will be some molecule at the bulk. Okay, so if I consider the molecule that is present at the bulk, that bulk molecule will be surrounded by all the other water molecules. Okay, so suppose this is the particle at the bulk, so this is surrounded symmetrically by all the particle, hence the net force of attraction on this molecule is negligible. But if you look at the surface molecule will experience only the force which is towards the downward direction because there are no water molecule present above it, everything which is present is below it. So we know that the surface molecule are always at a tension. Okay, now because the molecule collide with each other, they will impart energy to each other. If the energy of the molecules becomes sufficient, then it will come out from the liquid phase and enter into the vapor phase. Okay, so this property is known as escaping tendency of the molecule. Okay, so we know that there are so many molecules inside this container, they all will be colliding with each other, giving energy to each other. If some of the molecule gains energy and they come out of this liquid surface, then we will say that evaporation has started. Okay, so just let us look at this. So as you can see, initially the particles at the surface have sufficient kinetic energy to escape from the surface. Now suppose we close this container. So what will happen? You can clearly see that, okay, you can clearly see that the molecules are bouncing back in the liquid phase. Okay, so let me just play it again so that you understand it. Okay, let us look at this. So initially the water molecules were coming outside due to evaporation and it was escaping into the atmosphere. Now what we are going to do, we are going to close this. When we close this, the molecule cannot escape out, so eventually some molecule will bounce back and some will enter back into the solution. So at that point there would be a equilibrium that is established between the liquid and vapor. So we will say that at this point when there is an equilibrium between liquid and vapor, when the gas molecule which has escaped out is going back into the liquid and few molecules are coming out, at that point we will say that there is an equilibrium between liquid and vapor, and at that point rate of condensation will always be equal to rate of evaporation. So at this point when the liquid and vapor gets in equilibrium to each other, okay, so at this point when the liquid and vapor are in equilibrium with each other, so the pressure that would be exerted by the vapor molecule on the surface of this liquid is called as vapor pressure. Okay, so I hope you have understood this. So we are taking initially a beaker, that beaker had some water or any liquid, the surface molecule would start escaping out due to evaporation. Now when we close that particular container, what will happen? The molecule cannot escape out. So initially what would happen? There would be accumulation of vapor above the surface of the liquid. So the vapor would start accumulating above the surface of the liquid. Now as the accumulation process starts, the vapor molecule will start colliding with each other and they will have sufficient energy. Some of the molecule will go back into the liquid state, okay, so they can penetrate the surface and they will go back into the liquid state. So we'll say that condensation is happening. So at some time there would be an equilibrium between the vapor and the liquid. That means the vapor which is coming out, okay, is equal to the number of vapor that is condensing. So at that point, when the equilibrium is established, the pressure exerted by these vapor on the surface of the liquid is called as vapor pressure. Okay, so I hope this definition is clear to you. So basically we say that the pressure exerted by the vapor molecules on the surface of the liquid when liquid and vapor are in equilibrium is called as vapor pressure. Okay, so this is the basic idea of vapor pressure. So we are saying that we were having a container, a closed container, okay. So we were having a liquid. So the molecules of liquid were there, so I represented with L. Some vapor would be formed initially, okay. So how we can measure it? We'll just connect with a manometer, okay. Now when we connected the manometer, initially what would happen? Only vapors are forming. So those vapor would exert a pressure and the level of the mercury in the manometer would keep on increasing, okay. So let me just show it over here. So if I connect this with a, say, a manometer, so what would happen over here is, okay, suppose this is the manometer, so this is filled with mercury. So initially we will make sure that the entire container is evacuated, there is no gas molecule over here. So initially there would be no pressure recorded. So as soon as the vapor starts forming, it escapes from the surface of the liquid, it will go and exert some pressure on the mercury would rise from here. So the mercury level would keep on increasing, indicating that there are some vapors that is being formed. After some time it was observed that the height of the mercury becomes constant. So it is neither increasing nor decreasing. It doesn't mean that this process has stopped, it means that there has been a dynamic equilibrium that has been established. So what happened at that point is, vapor molecule were coming initially, so there was an accumulation of vapor molecule above the liquid surface. So these vapor would collide with each other. On collision they would have sufficient energy. Some vapor molecule would penetrate the surface and go back into the liquid. So we'll say that condensation is happening, okay. So at equilibrium what happens is, rate of condensation becomes equal to rate of evaporation. That means the number of molecules that are escaping out, okay, the number of molecules that are escaping out from the liquid becomes equal to the number of molecules that are condensing back into the liquid from the vapor state. So at that point we say that a equilibrium is established between liquid and vapor. Now few of the vapors will go and always exert a pressure on the surface of the liquid. That pressure is known as vapor pressure, okay. So we'll say that the pressure exerted by the vapor molecule on the surface of the liquid when liquid and vapor are in equilibrium is called as vapor pressure, okay. Now vapor pressure is clearly a intensive property, okay. I hope this is clear to everyone. Now let us look at the factors that affect vapor pressure, okay. So the first very important factor is the temperature, okay. Now as we increase the temperature, okay, as we increase the temperature, now we know that average kinetic energy of molecule is directly proportional to its temperature. So when we increase the temperature, the average kinetic energy of the molecule increases. So if the average kinetic energy of the molecule in the liquid phase increases, it will have more tendency to escape out, okay. So if we increase the temperature, we will always say that the escaping tendency of the molecule has increased because of its increase in kinetic energy. Hence more number of vapor would be formed. Now more is the number of vapor formed, more it will exert pressure on the surface, okay. So we will say that the vapor pressure has increased. So we directly say that on increasing the temperature, okay, on increasing the temperature, You can write it down. On increasing the temperature, the average kinetic energy of molecules increases. The average kinetic energy of molecules increases. Okay, on increasing the temperature, the average kinetic energy of molecule increases, and so does it. Hence, its escaping tendency also increases. Okay, because escaping tendency of molecule increases, more and more number of vapor would be formed. Therefore, vapor pressure would increase. Okay, so we'll say that therefore vapor pressure would increase. Okay, so on increasing the temperature, vapor pressure will always increase. On decreasing the temperature, we know that on decreasing the temperature, the average kinetic energy of the molecule will decrease. Hence, its tendency to escape out will decrease, because if you decrease the temperature, the molecules have less thermal energy. Now, because they have less thermal energy, they will not be able to come outside the liquid, okay, and come, basically it is not having the sufficient energy to get itself knocked out from the solution. Okay. So, if you look at the variation of vapor pressure with temperature, it is given by an equation known as Clausius-Clapeyron equation. So, if you look at the vapor pressure versus temperature graph, so you can see that on increasing the temperature, it increases. Okay, so there is an exponential type of increase. So, the variation of temperature, the variation of vapor pressure with temperature the variation of vapor pressure with temperature is given by Clausius-Clapeyron equation. Okay, so this is given by Clausius-Clapeyron equation. Okay, so this equation is something of the same format as that of Van 't Hoff equation or Arrhenius equation. Now, this says that ln P2 by P1 is equal to delta H vaporization upon R into 1 by T1 minus 1 by T2. Okay, so this is your Clausius-Clapeyron equation, where P2 is the vapor pressure at temperature T2, P1 is the vapor pressure at temperature T1, delta H vaporization is the enthalpy of vaporization of the liquid, R is the gas constant. Okay, so you can find out the vapor pressure at different temperature. You can clearly see that this is a exponential type of increase. Okay, so when you plot vapor pressure with temperature, so it will increase exponentially with increase in temperature. Okay, I hope you have understood this. You can write this down. Okay, hope this is clear to everyone now. So basically we say that on increasing the temperature, the vapor pressure will keep on increasing, and the variation of vapor pressure with temperature is given by an equation which is known as Clausius-Clapeyron equation. Okay, and Clausius-Clapeyron equation basically says that ln P2 by P1 is delta H vaporization upon R into 1 by T1 minus 1 by T2. Okay. The second very important factor on which vapor pressure would depend is nature of liquid. Now, this is obviously a very apparent result, or we can say that it is very obvious. Like, let us take an example of, say, ethanol. Okay. Now, since because you are doing a lot of sanitization at your home, you know that one of the most important constituent of a sanitizer is alcohol. Okay. Now, when you like put that sanitizer on your hand, so you can feel that there are alcohol on it, and that alcohol gets evaporated, due to which we feel the coldness on our hand, right. So, obviously ethanol is a volatile liquid. Okay. As soon as it is coming in air, it is getting vaporized. Okay. So, any substance whose boiling point is less, will be more volatile. Okay. Something like ethanol, you keep ethanol in air, okay, ethanol gets evaporated completely. Now, suppose you take water, you keep water over in a container, open container. Okay. We know that the entire water cannot be evaporated or cannot be converted into vapor by its own. It will take a lot of time for the entire amount of water to get evaporated. Okay. So, we will say that water is less volatile than ethanol, okay, because what happens in water is hydrogen bonded to each other. Water is a small molecule, they are hydrogen bonded to each other. Now because of this hydrogen bonding, okay, because of this hydrogen bonding, one water molecule is holding other water molecule from escaping outside the liquid solution, okay. So because of the interaction between the water molecule, each water molecule holds the other water molecule in changing into the vapor phase. So basically we say that any liquid in which intermolecular forces of attraction is stronger, okay, when intermolecular force of attraction is stronger, that means one molecule will hold the other molecule from escaping out. So if it is not escaping out, vapor formed will be in very less quantity, and so the vapor pressure would be very less. So we say that liquids having strong intermolecular forces of attraction, liquids having strong intermolecular forces of attraction would have less vapor pressure, okay, and would be less volatile, okay. Hope this is clear to everyone. This is a very basic example. Example could be say water and ethanol, okay. So if we look at ethanol C2H5OH and water, okay, so we can clearly say that ethanol is volatile in nature. So ethanol will form more vapor at any temperature as compared to water. So the vapor pressure exerted by ethanol would be more, okay. Now one doubt that comes in our mind is ethanol is also having a hydrogen bonding, but the extent of hydrogen bonding ethanol is small or it is weak, because in ethanol there is a carbon present over there. So we know that carbon is hydrophobic, okay, the carbon group is hydrophobic in nature, so basically they get repelled. So due to which we know that the hydrogen bonding between ethanol molecule is less, okay. So I hope this point is clear to everyone. So any liquid which is having strong intermolecular forces of attraction, something like strong hydrogen bonding or strong dipole-dipole interaction, will have less vapor pressure because the molecules will form strong bonds and will not allow each other to go outside the liquid solution and form the vapor. So basically we will say that two very important factors on which vapor pressure depends is temperature. On increasing the temperature, we will say that vapor pressure will always increase because the escaping tendency of the molecule increases due to increase in their kinetic energy. Second very important point is nature of the liquid. All the liquids which are able to form strong hydrogen bond or form strong intermolecular forces of attraction between them will always have less vapor pressure. A more volatile substance will always have a more vapor pressure, and a less volatile substance will always have less vapor pressure, okay. So I hope you have noted it down, okay. I hope this is clear to everyone. The third important factor is the addition of non-volatile solute, okay. Now suppose we are having a container, obviously we are talking about a closed container, because if we open the container the vapor will escape out and there would be no vapor pressure. Then the pressure exerted on the surface would be same as that of the atmospheric pressure. So the container has to be closed so that the vapor formed of the liquid is exerting pressure on the liquid surface, because if you open the container we will say that the vapor would escape and atmosphere would exert the pressure on the surface, which is also the atmospheric pressure, okay. Now suppose we are having a a liquid, okay, suppose we are having a solvent, a liquid solvent, say we call it as A, okay. So only liquid solvent is present, so what we know over here, there would be vapor. So I will show the vapor in blue dots. So we know that the vapor of this would be formed, okay. So the solvent, basically the particle at the surface would keep on crossing the barrier and would keep on escaping out, forming the vapor. Few vapor would also go back in the solution, and there would be equilibrium between the liquid and vapor. So there is a basically a equilibrium between liquid and vapor. Okay, so the molecules are coming out, few molecules are going in. So the pressure exerted by this vapor on the surface of the liquid is called as vapor pressure. Now suppose to this container we add some non-volatile substance or non-volatile solute. We have taken a non-volatile solute. Non-volatile means when you add this non-volatile solute, the solute won't form any vapor because it is non-volatile. So suppose if I have added the non-volatile solute to this container, okay. So we knew that this only had solvent initially, okay. Now this was our solvent, okay. The particle shown in red is our solvent. Now we have added a non-volatile solute. So basically what would happen, this non-volatile solute would go and distribute itself in the solvent homogeneously. So the solute would homogeneously spread into the solvent when a solution is made by mixing solvent and solute. So what would happen over here is some of the non-volatile solute which I am showing in purple would occupy the surface. Okay, so they would occupy the surface. So few of the non-volatile solute would occupy the surface. Okay, now you can see that initially only red dots were there. Okay, that means only solvent was present at the surface. Now along with the solvent, some of the non-volatile solute would also be present. Now we know that non-volatile solute cannot form vapor. Okay, so the number of liquid on the number of the molecules of solvent on the surface would decrease because the surface is now occupied by some of the solute molecules as well. So the number of solvent molecules at the surface decreases. Okay, so the number of the molecules that were escaping out has decreased. Now because this is a surface property, molecules from the surface are leaving, so we know that less number of vapor would be formed over here. Okay, less number of vapor would be formed over here. So we'll say that the vapor pressure has decreased. Okay, so when we add non-volatile solute, so we'll say that vapor pressure of liquid or the vapor pressure of solvent decreases. Okay, hope this is clear to you. So basically I am saying that when we are dissolving a non-volatile solute in a solvent, so the non-volatile solute will get distributed itself in the solvent. Okay, so the non-volatile solute would also occupy the surface. Now initially the surface was only occupied by the solvent molecules. Now it will also be occupied by the non-volatile solute which cannot escape out. So basically surface remains, the area of the surface remains the same. So the number of particles at the surface of the component that was volatile would decrease. So in this case the number of particles of solvent at the surface would decrease because some of the positions have been occupied by the non-volatile solute. So the number of solvent escaping out from the solution would decrease, hence the vapor pressure would also decrease. Okay, so these are the basic three factors on which vapor pressure depends. It depends upon the temperature. On increasing the temperature, we know that the vapor pressure of the liquid will always increase because its average kinetic energy increases and the escaping tendency increases. So the molecule at the surface can easily escape out. Now when we talk about nature of the liquid, all those liquid which are able to form strong intermolecular forces of attraction or strong hydrogen bonding will not escape out easily and hence will have lower vapor pressure. Third is the addition of non-volatile solute. When we add non-volatile solute, what would happen? The surface would be occupied by some of the non-volatile solute also. So the number of solvent molecules that were escaping out from the surface would decrease, resulting in the decrease in the vapor pressure. So these are the three very important factors on which the vapor pressure depends. Okay. Now let me ask you one question over here. Okay, now this is a very important question that can come over here. Okay, so whenever I set a paper, I basically set the paper on the logical side where I am able to extract the conceptual depth of the student. Okay, so my question is, suppose we are having a small container. Okay, suppose we are having say 1 kg of water in it. Okay, suppose we are having 1 kg of water in it. So it is a closed container, so there would be some vapor formed, so this would exert a vapor pressure. Now I poured this 1 kg of water in a container that was bigger in size. So I can clearly say that now this would be the height would decrease. Okay, so this is the 1 kg of water now. So I am saying that I had a small container, I added 1 kg of water in it, I would have some vapor pressure over here. Okay, so I could record the vapor pressure. Now I poured this entire 1 kg of water in a bigger container. Okay, so what would happen to the vapor pressure? Would vapor pressure change? It would remain same, okay, or it would increase or decrease? Now the first thing that comes in our mind is, now initially the surface area was less, okay, because this was in a more compact cylinder. Now we have taken it in a big cylinder, so we can clearly say that the surface area increases. Okay, so basically if you look at the area of the surface, that has increased. Now we know that evaporation is a surface phenomena, so more is the surface area, easily the molecule can escape out. So from that point of view, I can say that because we have increased the surface, so more number of molecules will be present at the surface, so more would be their escaping tendency and more should be the vapor pressure. But vapor pressure was not that. When you have increased the surface, so the number of molecules that were escaping out in the vapor phase would be more, but because you have increased the surface area, so number of molecules that are condensing back would also increase. So that would result in no change. So basically if I increase the surface area, there would be no change in the vapor pressure, it would remain the same. Okay, vapor pressure will change only when I have changed the temperature. Okay, I hope this point is clear to everyone. So if I take 1 kg of water, or I take 2 kg of water, or I take 5 kg of water, vapor pressure at a given temperature will always be same. Okay, even though you increase the surface area, still the vapor pressure would be same at a particular temperature. Okay, now if you are decreasing or increasing the pressure, the next thing comes is, suppose we are having a container. Okay, we are having a movable piston. So if we are increasing or decreasing the pressure, okay, so if we are increasing or decreasing the pressure, will there be any change in the vapor pressure? Again, vapor pressure will not be dependent on that, because it is again temperature dependent. Okay, so we will say that it is independent of pressure also. Okay, I hope this is clear to everyone. So a very important and a fundamental question that comes on this portion is, suppose we are having a container, okay, which is fixed, or let us assume that it is having a movable piston on it. Okay, so we are having a container which is fitted with a movable piston. Okay, so we are having a movable piston. Now suppose I say that there is a gas inside this. Okay, now say, and there is some water also. Okay, I hope this diagram is clear to everyone. So we are having a cylinder, okay, fitted with a moving piston. It has a gas and some water. So it has been told that the total pressure developed inside the container is, suppose, 200 mm of Hg. Okay, so the total pressure, okay, inside the system is 200 mm of Hg. So now what this total pressure is, basically there is a gas molecule inside, so the gas molecule will exert the pressure. Now because there is a liquid water as well, okay, so the liquid water will evaporate, okay, and will form some vapor. Okay, now that vapor will also exert some pressure on the surface of the liquid, that is known as the vapor pressure of the liquid. So this basically, the system above the surface of the liquid will have gas, as well as the vapor of the liquid. So the total pressure exerted would be the pressure exerted by the gas plus vapor pressure of the liquid. Okay, I hope this is clear to everyone. Okay, because the space above the surface of the liquid would have gas as well as the vapor of this liquid. So vapor of this liquid will exert a pressure, gas would also exert a pressure, the total pressure would be pressure of gas plus vapor pressure of the liquid. Now suppose the vapor pressure of the liquid was given to us as say 50 mm of Hg. Okay, so it is given 50 mm of Hg. So the pressure exerted by the gas would be 150 mm of Hg. Okay, I hope this is clear. Now suppose what I do is I compress this entire system. Okay, I start pressing the piston downwards so that the pressure inside increases. So I am compressing the system to 1/3 of its original volume. Okay, so I am compressing the piston to 1/3 of its original volume. So what would be the new pressure? Okay, so just solve this now. So I am just pressing the piston and compressing the entire system to 1/3 of its volume. So the question is asking find the new total pressure. Okay, so what would happen when I start compressing it? Okay, because we know that the wave pressure is independent of the pressure, so the wave pressure won't change over here. Now when we are just compressing this gas, okay, so we'll assume that this gas behaves as ideally. So we know that temperature is fixed, so PV is equals to nRT. N is fixed because it is in a fixed container. Okay, T is fixed, so I will say that pressure is inversely proportional to volume. So if I compressing the volume, okay, to 1/3 of its original volume, the pressure of the gas would increase 3 times. So on compressing, the pressure of this gas would become 3 times of that of its original pressure. So this would become 450 mm. Okay, but the wave pressure would remain same 50 mm only. Okay, because it is independent of pressure. So the total pressure exerted now would be 500 mm. So again a very important and a very conceptual question that can come over here. Okay. Now I remember when I was teaching this concept, someone in my class asked me, sir, when I am applying the pressure, so obviously the vapor present over the surface of the liquid is getting some energy. So if that gets energy, it should go inside the liquid, so it should also condense and the vapor pressure should also decrease. Now obviously he was right partially, but the other scenario he couldn't understand. So when we are just exerting the pressure, the vapor above the surface of the liquid will definitely gain some energy because we have pressed this, so they will gain energy, they will go inside. But when they go inside, okay, they will go inside with lot of force or with lot of momentum, so they will knock out some other molecules that is present in the liquid and they will come out because they will get the energy from the molecules that are coming inside. So when you press that, molecules above the liquid, that is vapor, gets energy, they go inside the liquid. Now when they go inside the liquid, they transfer the energy to some other, okay, liquid molecule. Now those liquid molecule will escape and the net number of molecule that is going inside and that is coming out will remain same. So the vapor pressure doesn't change. Okay, so this is again a very beautiful question that is based on pure concepts, and these questions can definitely come in JEE Advanced. Okay, so just write it down. So basically this question said that we were having a container fitted with a movable piston. We had a gas inside it and a water. Okay, the water has a vapor pressure of 50 mm of Hg and the total pressure inside the container was 200 mm of Hg. So from that data we calculated the pressure of gas, that came out to be 150 mm of Hg. We have assumed that the gas is ideal in nature. So when we compress the system or when we press the piston downwards and compress the system to 1/3 of its original volume, so we know that vapor pressure won't change because we have changing the volume to 1/3 of its original value. So the pressure of ideal gas would increase 3 times and the pressure would become 450 from 150 and vapor pressure would remain same. So the total pressure in this case would be 500 mm of Hg. Okay, I hope this is clear to everyone. Okay, so next important concept that we wanted to discuss today is Raoult's law. Okay, So we'll understand Raoult's law, we'll do some numerical solving on Raoult's law. Now Raoult's law state that a solvent partial pressure in a solution or mixture is always equal to the vapor pressure of the pure solvent multiplied by its mole fraction in the solution. Okay. So what I am saying over here is, suppose I am having a container. Okay. In this chapter, whenever I am saying container, obviously I mean a closed container. So if sometimes I don't draw as a closed container, just understand it that it is a closed container, because if it is not closed, then the vapor would escape out and the concept of vapor pressure would suddenly disappear. Okay. So I am saying that suppose I am having a solvent in it. Okay, let me label that solvent as A. Okay, so initially what would be there? Only the vapor pressure of solvent would be there. So I will call this as P naught A. So P naught A is the vapor pressure of pure solvent. Okay, vapor pressure of pure solvent. So initially I will be having only pure, like vapor pressure of pure solvent, because there is no other component present. Now suppose if I add some solute to it. Okay, now we know that when we are adding some solute to it, so the vapor pressure of the solvent would decrease. Okay. So when we are adding a non-volatile solute, so we know that the surface will be occupied by a solute molecule. So the number of solvent molecules on the surface of the liquid will decrease. So when the number of the solvent molecule decreases on the surface, less number of vapor would be formed and the vapor pressure would decrease. Okay. Now let that pressure be PA. Okay. So this would be the vapor pressure of the solution. Okay. Now the solution basically comprises of solvent and in this case a non-volatile solute. So I say that the pressure exerted by the vapor of the solvent, the pressure exerted, the vapor pressure or the pressure exerted by the vapor of the, okay, suppose this is, I hope you have understood that this is the vapor phase. So I will say that the vapor pressure in a solution, okay, will always be equal to the product of vapor pressure of pure component into its mole fraction in the liquid phase. Okay. So XA is basically mole fraction of A in liquid phase. Okay. So you can clearly see that this expression will work if XA is 1. If XA is 1, it means that it is having only one component. Okay. So whenever there is only one component, the vapor that would be formed above the surface of the liquid would be of that of a pure solvent only. So when XA is 1, so PA will be equal to P naught A. Okay. So the pressure developed over the liquid will be due to only A and that would be P naught A. Now when we have mixed some solute over this, okay, so we know that the vapor pressure would decrease. So let the pressure over the solution is now PA. Now the pressure over the solution due to that solvent component will always be proportional to its mole fraction in the liquid phase. Okay. So I am saying that the vapor pressure of the solvent, okay, the vapor pressure of the solvent in the mixture of a liquid will always be proportional to the mole fraction of the solvent in the liquid phase. Mole is the mole fraction of the solvent in the liquid phase. That means mole would be the number of particles at the surface of the liquid and hence mole would be the escaping tendency and hence mole would be the vapor pressure. So mole is the number of particles of the solvent, mole would be its vapor pressure. Okay. So I will say that the pressure exerted, okay, over the solution, the pressure exerted over the solution is always proportional to the mole fraction of the solvent. Okay. So when I remove this proportional sign, I will get P naught A. So P is equals to P naught A into XA is the expression for Raoult's law. Now you should understand one thing, that Raoult's law is not applicable at all conditions. Raoult's law is applicable only for dilute solutions. Okay. Because once you start increasing the concentration, we know that the particles will start interacting and the vapor pressure would change abruptly. So Raoult's law is applicable only for solutions that are very dilute. Okay, so this is basically defined for dilute solutions. So Raoult's law states that whenever we are having mixture of liquids, okay, the vapor pressure developed over the solution due to one of the component will always be proportional to the mole fraction of that component in the liquid phase. More is the mole fraction, or more is the number of molecules or particles of that in the liquid phase, the more number of vapor it can form. Okay, so we will say that pressure is always proportional to the mole fraction. So pressure would be always be equal to P naught A into XA. That is what it says. Partial pressure in a solution is equal to the vapor pressure of the pure solvent multiplied by its mole fraction in the solution. Okay, so just remember this, XA is mole fraction in the liquid phase, P naught A is the vapor pressure of pure A, PA is the vapor pressure when we have mixed another component in the pure solvent A. Okay, so I hope this is clear to everyone. Okay, so if we plot this, so we know that if we plot vapor pressure versus mole fraction, so we have said that PA is equal to P naught A into XA, right. So when XA is equals to 1, XA equals to 1 means that we are having only one component, A we have chosen as solvent, so we will say that we are having only solvent. Okay, so the pressure exerted would be equal to P naught A because it is only a pure solvent. So if you plot this vapor pressure versus mole fraction, okay, so the mole fraction is increasing, the mole fraction of XA is 0 over here and mole fraction of XA is 1. That means at this point we are having only A, and at this point we are having only the other component, that is B. Okay, so when XA value is 0, we know that the pressure, okay, due to the solvent, the vapor pressure due to solvent would be 0, because when XA is 0, the partial pressure of A or the pressure exerted over the solution by A would be 0. Now when XA is 1, so P will be equal to P naught A. So at XA equal to 0, we know that the partial pressure would be 0 or the vapor pressure would be 0, and XA equals to 1, the partial pressure would be this. So let this corresponds to P naught A. So this is basically your Raoult's line. Okay, so if you connect this, this is your Raoult's line. Okay, so if you keep on decreasing the mole fraction of A, so if you look, you are decreasing the mole fraction of A, so the vapor pressure of the solution also decreases for dilute solutions. Okay, so I hope this is clear to everyone. So just look at this expression. Okay, so just let me write it once again. So suppose we are having a liquid, okay, and we are having some vapor of this liquid. Okay, so suppose this is only pure liquid, so I will say that the pressure exerted is P naught into P naught L. P naught L is the vapor pressure of the pure liquid. Now suppose I have added some solute to this. Now because I have added some solute to this, we know that the number of, okay, L molecules escaping out would decrease because the surface would be occupied by the solute as well. So let the vapor pressure exerted by the L, okay, by the liquid L over the solution would be proportional to the mole fraction of L in the liquid state. So I will say that PL is equals to XL into P naught L. Okay, so this is basically your Raoult's law. Hope this is clear to everyone. Okay, so one thing which I can do over here is I will say that P is equals to P naught A into XA. Okay, so I can also write XA as, if suppose there are two components A and B, so XA plus XB is 1. So I can write XA as 1 minus XB. So I can write this as P equal to P naught A minus P naught A into XB. Okay, so I will write this as P naught A minus P equal to P naught A into XB. Okay, so I can write XB as P naught A minus P upon P naught A. Okay, so Xb is basically mole fraction of solute, because I have already told you that we have assumed that A is the solvent and B is the solute. So A is the solvent and B is the solute. Okay, so if to a solvent A we are adding a solute B, okay, so initially only solvent was present, so the vapor formed would be of solvent only, so the vapor pressure would correspond to vapor pressure of pure A. Now when we have added a solute B to this, so we know that the surface will be occupied by the solute B now as well as the solvent A, so the number of particles of solvent A would decrease on the surface and hence the vapor pressure would decrease. So the pressure exerted over the solution by the solvent would be P naught A into XA. Okay, so we know that the pressure would decrease, so P naught A minus PA would be decrease in the vapor pressure. Okay, so basically this quantity P naught minus P is known as decrease in the vapor pressure. Okay, so this is called as decrease or lowering in vapor pressure. Okay, we can call this as decrease in vapor pressure or lowering in vapor pressure. Now when we divide this with P naught, so this becomes relative lowering in vapor pressure. Okay, so this is relative lowering in vapor pressure. Okay, hope this concept is clear to you and hope Raoult's law is clear to everyone now. So just write it down quickly. So I will say that relative lowering in vapor pressure is always equal to the mole fraction of solute. Okay, just write it down quickly. Okay, so let us solve some question on this. Now this says that at 25 degrees Celsius, the vapor pressure of methyl alcohol is 96 torr. What is the mole fraction of methanol in the solution in which the partial vapor pressure of methanol is 23 torr? Okay, so obviously we have understood the question. This is saying that the vapor pressure of methyl alcohol, that is vapor pressure of pure methyl alcohol, is given to us as 96 torr. Okay, now we have added some solute to it. Now because we have added the solute to it, we know that the surface of this solvent would also be now occupied by the solute, so the number of particles at the surface of the solvent would decrease and hence the number of particles escaping out will decrease, and so the vapor pressure would also decrease. So once we have added that, so we know that the vapor pressure over the solution becomes 23 torr. Okay, so this is asking what is the mole fraction of methanol. So we will say that P is equals to P naught into mole fraction of methanol. Okay, so the pressure above is 23, this is 96 into mole fraction of methanol. So we will get the mole fraction of methanol as 23 upon 96. So straightforward question just based on the basic data. Okay, so I hope this is clear to everyone, so nothing difficult. Now let us look at this question. It says that the vapor pressure of two volatile liquids is Pt is equal to 5.3 minus 2 xb in centimeter of Hg, where xb is the mole fraction of B in mixture. What are the vapor pressure of pure liquids A and B? Okay, so expression has been given to us as Pt, which is 5.3 minus 2 xb. Okay, we need to find the vapor pressure of pure A and B. So when only A is present, okay, pure A means only A is present. Now when only A is present, it means that XA will be 1. Now when XA is 1, so it means that XB will be 0. So when XB is 0, the pressure would correspond to pure A, so that would be 5.3 centimeter of Hg. Okay. Now if we want to find the vapor pressure of pure B, so when pure B is there, that means only B is present. Now when only B is present, it means that the mole fraction of B would be 1. Now if the mole fraction of B is 1, then the mole fraction of A would be 0. Okay, so if we put the value of mole fraction of B as 1, so we will get the pressure of pure B, which is 5.3 minus 2, that is 3.3 mm of Hg. Okay, so again a very easy level question, just we are manipulating the data and solving it. Okay, so don't worry, the level of the question will keep on increasing. So we want to touch all level of questions. So that is why we are starting with the basic subjective level questions. Okay. Next comes is the addition of non-volatile solute. Now I've already told you this, that if suppose we are having only solvent, okay, which we have calling it as A, so the vapor formed would be only of A, so that would be rich only in A, so we can call the vapor pressure as P naught A, that is vapor pressure of pure solvent. Now when we are adding non-volatile solute, now we know that when we are adding a solute, so the solute will get distributed in the solution, so there would be some solute that would come at the surface, okay, replacing some of the solvent, okay. So the number of solvent particles at the surface would decrease, so the vapor pressure at the vapor pressure would also decrease, the pressure exerted by the vapor would also decrease, because the number of molecules that are escaping out has decreased. So now let the P be the vapor pressure over the solution, so we know that that will be proportional to the mole fraction of the volatile component in the liquid phase, so that is proportional to P, that is proportional to XA. So when you remove this proportional sign, we got this as P naught A into XA, okay. So I can write this as P by P naught A is equal to XA, I can write this as 1 minus XB, or B is also the solute over here, so we have added B, which is solute, okay. So we know that XA plus XB is 1, so XA basically here is solvent, so X solvent plus X solute is 1, so I can write X solvent as 1 minus X solute, so I can write X solute as 1 minus P upon P naught A, so I will write this as P naught A minus P upon P naught A, this is equal to mole fraction of solute, okay. So P naught A was the pressure of pure A, P was the vapor pressure when a solute has been added to it, a non-volatile solute. So P naught A minus P represents the lowering of vapor pressure when the solute has been added to it, and when you divide with the vapor pressure of pure, so it becomes a relative lowering in vapor pressure. Now we have already done this, we have already derived this, okay. So now let's solve this question. Now this says that the vapor pressure of pure water at 26 degrees Celsius is 25.21. So I know that the vapor pressure of P naught basically represents the pure form. P naught water is equal to 25.21 torr. Okay, what is the vapor pressure of the solution which contains 20 gram glucose in 70 gram of water? Okay, so we know that sucrose is the molar mass of glucose, glucose has been given to us as 180 gram per mole. So the mole fraction of the moles of glucose would be its mass upon molar mass. Okay, similarly molar mass of water we know is 18 gram per mole. Okay, so the mole fraction of water, the moles of water in this case would be 70 upon 18. Okay, so the total moles we know over here is 20 upon 180 plus 70 upon 18. Okay, so I can write this as 1 by 9 plus 35 by 9. Okay, so I can write this as 36 by 9, that is 4. So the total number of moles of all the components in the solution is 4. So the mole fraction of water in this case would be moles of water, which is 35 by 9 divided by 35 by 9 divided by total moles. Okay, so just we are finding out the mole fraction of water, so this would be 35 upon 36. Okay, so the mole fraction of water in the solution is 35 by 36. Now we want to find the vapor pressure over the solution when 20 gram of glucose is added to 70 gram of water. So we know that P is basically equal to P naught of water into X of water. Okay, water is the only volatile component. So we know the value of P naught as 25.21, we know the mole fraction 35 by 36. So we'll just multiply, we'll get the value of P. P is basically the pressure over the vapor pressure over the solution. Okay. Now that has clearly decreased because we have added a non-volatile glucose in the solvent. Okay. So just let us solve this now. I hope you are writing the question or you are taking the snapshot so that you are adjusting it in your notes. Now this says that the vapor pressure of pure water is given to us as 23.76. The vapor pressure of the solution containing 5.4 gram of a non-volatile substance in 90 gram of water is 23.32. Calculate the molecular weight of the solute. Okay. So on reading the question, the first thing which you should do is extract the data. So we know that the vapor pressure of pure water has been given to us as 23.76 torr. Now when we have added a non-volatile solute, we know that the vapor pressure would decrease, and now the pressure over the solution or the vapor pressure over the solution is 23.32 torr. Okay, we have taken 90 gram of water, so we can write the moles of water. Moles of water would be mass of water divided by its molar mass, which is 5. We know the moles of solute would be mass of solute upon its molar mass. Let the molar mass of the solute be capital M. Okay, so the number of moles of solute would be 5.4 upon M. So we know the mole fraction of solute now and mole fraction of solvent. Okay, solvent over here is water. So the mole fraction of solvent would be moles of solvent divided by total moles. Total mole would be moles of water plus moles of solute, or moles of solute plus moles of solvent. Okay, so this we got. Now we know that P naught minus P upon P naught was equal to mole fraction of solute. Okay, hope you have understood this. So P naught over here is 23.76 minus 23.32 divided by 23.76. So X solute would be 5.4 moles of solute upon total moles. Total moles was 5 plus 5.4 M. Okay, so just you have to solve this, you will get the value of M, the molar mass of the unknown solute. Okay, so I am leaving the steps to you. I hope after the class you are solving these questions and you are getting the right answers. Okay, so these are basic calculations. So I think you should practice this so that you become well versed with it. Many questions in JEE Advanced, especially the integer type question, will be based on such type where you have to do a lot of calculations. Okay, so hope this is clear to everyone. Okay, now just let us try the third question. So this says that there are there is some word written over there, ideal solution. Just leave it for now because in the next lecture we are going to study about the solutions, ideal and real solutions. So it says that A and B forms ideal solution. At 300 Kelvin, the vapor pressure of the solution containing 1 mole of A and 3 moles of B is this much. At the same temperature, if 1 more mole of B is added to the solution, the vapor pressure of the solution increases by 10 mm. Determine the vapor pressure of A and B in the pure state. Okay, just do it quickly. We have been given number of moles of A, number of moles of B. So the mole fraction of A in that case would be 1 by 4 and the mole fraction of B, okay, because 1 mole of A and 3 mole of B is given to you. So total moles initially was 4. So mole fraction of A would be number of moles of A divided by total moles. Okay, mole fraction of B would be number of moles of B upon total moles. Okay, we have to find the vapor pressure of pure A and B. Okay. Okay, for this question we are going to use Pt is equals to P naught A XA plus P naught B XB. Okay. So just wait a minute, I will just explain you this before we can solve this question. Again a very easy question. So let us first study the Raoult's law for binary solution and then we will get back to this question. Okay. Now suppose we are having two components. Okay, now we are taking two components in the liquid and both of them are volatile. Till now what we were saying that we were having a volatile solvent and a non-volatile solute. So the vapor formed was only of the solvent, and solute was not forming the vapor because it was non-volatile. Now we are taking both the components as volatile. Okay, so we are mixing two volatile components. Suppose A is this shown by like pink ball and B is the shown by purple. So basically we are having two components. You can clearly see there are two colors, so there are two components over here. So we have mixed two components and both the components are volatile. Okay, so both components are volatile. Okay, so you can clearly see that vapor of both the components are formed above the solution. Obviously this jar is closed. Okay, so when we are mixing two liquids A and B, both of them are volatile, so the vapor of both the components would be formed. Okay, so A is your pink, B is your purple. Okay, so the vapor of both the component has been formed. Now the first thing which we want to discuss over here is the total pressure exerted. So all of these vapor will go and exert some pressure on the surface. Okay, so we want to find the total vapor pressure. So clearly the total vapor pressure would be the sum of the partial pressure of each of the vapors. Okay, so let us say that we are having in a container we are having already. So we'll have, say we had XA as the mole fraction of A and XB as the mole fraction of B. So suppose we mixed Na moles of A with Nb moles of B. We mixed Na moles of A with Nb moles of B. So both the components were volatile, both the components form the vapor. So we knew the mole fraction of A and B in the liquid phase, that would be moles of A upon total moles. Mole fraction of B would be moles of B upon total moles. Okay, hope this is clear to everyone. So the partial pressure, the partial vapor pressure of A would be proportional to the mole fraction of A in the liquid phase, because A is forming the vapor. Okay, now we know that the vapor pressure, okay, depends upon the mole fraction of that component in the liquid phase. More is the component in the liquid phase, more would be the vapor formed. So the partial pressure or the vapor pressure exerted by A will be proportional to the mole fraction of A in the liquid phase. So XA is the mole fraction of A in liquid phase. Okay, XB is the mole fraction of B in the liquid phase. Okay, so I will say that PA is equal to P naught A into XA. Okay, because Raoult's law is obeyed. Similarly, we will say that the partial pressure or the vapor pressure exerted by B would be proportional to the mole fraction of B in liquid phase. So I can write partial pressure or the vapor pressure exerted by B is P naught B into XB. So the total pressure exerted over the solution would be the sum of the partial vapor pressure of both the components. So I will say that the total pressure exerted is P naught A XA plus P naught B XB. Okay, hope this is clear to everyone. XA is the mole fraction of A. I have already written this, hope you have marked it. So I am already saying that this is the mole fraction of A in liquid phase and XB is the mole fraction of B in the liquid phase. Okay, hope this is clear to everyone. So the total pressure exerted by the vapor over the solution of two volatile liquids will be the sum of their partial pressures or the sum of their partial vapor pressure. Okay, so the total pressure above the solution would be P naught A XA plus P naught B XB. Okay, because A is also forming the vapor and B is also forming the vapor. So the partial pressure of A would be P naught A into XA and the partial pressure of B over the solution would be P naught B into XB. So the total pressure would be the sum of the partial vapor pressure. Okay, now we are calling this as partial vapor pressure. When only one component was present, we are saying that it is a vapor pressure. Now if more than one component is present, so each component will exert some pressure. So that pressure is known as partial. Okay, total and a partial pressure. Okay, hope this is clear to everyone. So just write it down. You can write it over here. P naught A was the pressure of pure A. Okay, so this was the vapor pressure of pure A. P naught B was the vapor pressure of pure B. Okay, so this is vapor pressure of pure B. This is vapor pressure of pure A. Okay, XA was the mole fraction of A in liquid phase, XB was the mole fraction of B in the liquid phase. Okay, hope this is clear to everyone now. So we are mixing two components, both the components are volatile, vapor of both the components will be formed, so they will exert some pressure on the surface of the solution. So we will say that the total pressure exerted over the surface of the solution would be the sum of their partial vapor pressure. So the pressure exerted by A would be P naught A into XA, pressure exerted by B would be P naught B into XB. Okay, so just now let us enter into this question. Okay, now let's just solve it now. This is just formula based now. Okay, so we know that we are mixed two solutions, 1 mole of A and 3 moles of B are mixed together. The pressure over the solution is 550. So we know that the pressure over the solution is 550. Let the pressure of pure A be P naught A. So the XA we have already know is 1 by 4 and XB is 3 by 4. Okay, so I will get an equation P naught A plus 3 P naught B will be equal to 2200. So this is the first equation that I am going to form. Okay, now I am saying that at the same temperature if 1 mole of B is added. Now if we add 1 mole of B, so I will say that the number of moles of B becomes 4 because there were already 3 moles of A, 3 moles of B, and the number of moles of A remains same, that is 1. So the total moles would become 5. So mole fraction of A in this case would be moles of A upon total moles. Mole fraction of B would be moles of B upon total mole. Okay. Now when we added 1 mole of B, it is saying that the vapor pressure of the mixture increased by 10 mm. So we know that Pt is equals to P naught A XA plus P naught B XB. So we know that pressure is of pure component is P naught A, mole fraction is 1 by 5 plus P naught B into XB, XB is 4 by 5. So this is equal to the vapor pressure increased by 10. So this is 560. Okay, the vapor pressure increased by 10. So I will say that P naught A plus 4 P naught B will be equal to 2800. Okay, so these are the two equations that we are forming. So obviously there are two equations, two unknown. So just subtract 1 from 2. So we will be left with only P naught B. So P naught B will get as 600. So just plug the value of P naught B. So we will get the value of, in any of the equation we will get the value of P naught A as 400. Okay, so the answer would be 400 and 600. Okay, so straightforward question. It was asked in NEET. Okay, it was asked in AIMS. It was also asked in JEE Means. So straightforward question just based on the formula. Okay, so if you are through with the theory, if you are doing a very good analysis of the theory and you are doing a lot of subjective solving, then numerical solving becomes very easy. Don't neglect the subjective solving aspect. IIT is not about just cracking any objective question, or any competitive exam is not about cracking a objective question. The purpose of the competitive exam is to make you go deep in the subject, understand the conceptual portion, bring the important features of that particular subject and then analyze it for your application in the problems. That only will help you build up a very good skills and you will eventually become more and more confident in the subject. We are less confident when we are not doing subjective approach questions, because subjective questions are little lengthier to read, difficult to extract data, calculations are needed. But once we are thorough with this, the level of confidence will increase. Okay. So this was the formula that we derived. So if I want to plot the total pressure graph now, okay, because we are having two component A and B, so we will plot the total pressure along with the mole fraction. So we are taking again vapor pressure on the y axis and mole fraction on the x axis. So suppose we say that we are if we are going from left to right, the mole fraction of A is increasing. That means at this point we are having only A Okay, so at this point we are having only A. Okay. Now because at this point XA is 0, it means that XB would be 1 over here. Okay, because there are two components now. So I will say that only B is present at this point. So at this point only B is present, at this point only A is present. Okay. Now I can say that if XA is increasing from 0 to 1, XB will be increasing over here because XB would be 0 over here, because XA is 1 and XA is 0 over here, so XB would be 1. So XB is increasing over here and XA is increasing over here. So if we plot according to Raoult's law, if we look only at the pure component A, okay, so we know that the pressure of the partial wave pressure of pure component A would be P naught A into XA. So if XA is 1, pressure would be P naught A. If XA is 0, pressure would be 0. So the graph would look something like this. Okay, so here the value of XA is 0. So the pressure due to the partial pressure of A is 0, the partial wave pressure of A is 0. XA is 1 over here. So the partial pressure at that point is P naught A. Similarly, if we want to draw the curve for B, so we know that at this point XB is 0, that means the pressure, the partial pressure or the partial vapor pressure of B would be 0. Now at this point XB is 1, so it means that the partial pressure would be equal to the pressure of pure B. Okay, so this is the individual Raoult's law line for component A and B. Okay, so these are individual lines. Now when we want to calculate the total, so the total will be represented by this line. Okay, so this line, okay, this black line represents the total vapor pressure. Okay, so this is the graph. Again a very important graph, just draw it quickly. Okay, so let me just ask you one question over here. This is actually very simple and a conceptual question. Now suppose I draw a line over here. Okay, now this represents point A, the line where it intersects the wave pressure of A, it represents B, and the point where it intersects the graph of wave pressure of B with mole fraction represents C, and this point represents D. Okay, so what is AD? Okay, so what is AD? So AD will basically be at this composition, okay, composition, like we can get the composition of A and B at this point by looking at the graph. So AD would represent the total, okay, so AD would represent, I hope this is clear to everyone. So AD, if you just go over here, so AD would basically represents the total vapor pressure of the solution. Okay, so AD is representing total vapor pressure. Okay, hope this is clear to you. Similarly, if you look at BD, okay, so if you look at BD, what is BD? B is basically we are just drawing the line for, okay, obeying the Raoult's law for component A. So B was the point on the Raoult's law graph of A. So BD represents the partial vapor pressure of A at this composition, okay, because we are intersecting the Raoult's graph of component A. So BD represents the partial pressure of the partial vapor pressure due to A. Now if you look at CD, now what does CD represent? Because CD, this graph that was shown on the green line, this is basically for the B component, so that is the variation of the wave pressure of B with composition. So CD basically would represent the wave pressure of component B at this composition. Okay, so CD over here would represent the vapor pressure of B at that concentration. Okay, or I can say it represents partial vapor pressure of B, and BD represents partial vapor pressure of A, and AD represents total pressure. So we will say that the total pressure is equal to partial pressure of vapor pressure of A plus partial vapor pressure of B. So when I put this, so I will say that AD is equals to BD plus CD. Again, a very important question can come on this. Hope this graph is clear to everyone. Okay, so I hope this graph is clear to everyone. So this is basically the Raoult's law for a binary mixture in which both the components are volatile. Okay, so what we have done till now is we have just introduced the concept of vapor pressure. Vapor pressure is a very important concept because it is going to be used in colligative properties as well. The second thing which we did today was what is Raoult's law and how do we calculate the vapor pressure over the solution. Okay, when a non-volatile solute is added, we did a very important concept of lowering of vapor pressure and relative lowering of vapor pressure, and after that we did was mixing of two components that both of them were volatile, so that both of them forms the vapor over the solution. So we calculated the total pressure that would be exerted over the solution when two volatile components are mixed. I hope this lecture is clear to everyone. You can, if you are having just any issue, just you can solve those questions again. Okay, just read the theory which we have done today. You can consult NCERT or any theory book that you are referring to. So this is again a very important chapter. Every year a JEE advanced question is coming on this. So these are basically the foundation lecture. The level of difficulty would definitely increase from the next lecture. We are going to do lot of in-depth detailed analysis of few of the cases, and then we are going to do some high level problem solving. Okay, so I hope this lecture was interesting to you and I hope you have understood the concepts